Welcome back to the Nocturnal Astronomer. I'm your host, Atlas Reed. This is a place for quiet minds and deep thinkers. A space for anyone who has ever found that the scale, mystery, and wonder of the universe has a way of making earthly worries feel a little smaller. Tonight, we're doing something a little different. We're going to look back at the moments when our corner of the cosmos came much closer to disaster than most people ever realize. And I think you'll find, as we go, that the story these moments tell isn't one of dread. It's one of perspective, of quiet reassurance, of just how extraordinary it is that we are here at all, looking up at all of this. Let's dive in. Part 1. The Asteroid That Grazed Us. In 2013, a rock roughly the size of a 6-story building entered Earth's atmosphere over the Russian city of Chelyabinsk. It arrived without warning. Most people had no idea it was coming until the sky turned impossibly bright above them. The object released energy roughly equivalent to 30 times that of the atomic bomb dropped on Hiroshima. But because it exploded high in the atmosphere, around 30 kilometers above the ground, most of that energy dissipated before reaching the surface below. The main injuries on the ground came not from fire or impact, but from shattered glass. People had moved to windows, drawn by that strange morning light, and the shockwave that followed caught many of them off guard, sending glass inward across the city. Around 1,500 people sought medical attention that day. Considering the object's energy release, that number is, in the quietest sense of the word, remarkable. The atmosphere had done its job, and the planet had taken something large without breaking stride. What I find soothing about this is not that it was small. It wasn't entirely small. It's that the planet has been absorbing moments like this for 4.5 billion years. Earth is, in many ways, very good at this. It has had a lot of practice. What made Chelyabinsk genuinely surprising to astronomers was that it wasn't the asteroid they had been watching that day. On the very same morning, a separate, much larger asteroid, one roughly half the size of a football field, passed closer to Earth than our own weather satellites. Two unrelated objects arriving from different directions on the same day. Astronomers confirmed afterward that this was pure coincidence. There was no gravitational connection between them, no shared origin. The universe had simply, quietly sent two things past us at once. The larger object, the one scientists had been tracking, missed Earth by a distance that, in cosmic terms, is almost nothing. In human terms, it passed closer than the ring of satellites we use to check our weather every single day. it moved through that band and kept going. That image has always struck me as oddly reassuring, not alarming. The satellite ring is still there. The weather forecasts still run. The asteroid simply passed through a gap we use for our own infrastructure and continued on into the dark. These two events together, on a single ordinary Tuesday morning, reminded astronomers that the solar system is still very much an active place, and yet here we are, quietly, calmly discussing it under a blanket of night, as if nothing happened, because really, nothing did. Part 2. The Sun's Quiet Fury. In 1859, the most powerful geomagnetic storm ever recorded in human history struck the Earth. It came from the Sun, as most such storms do, but this one was in a category largely unlike anything before or since in the era of modern technology. A British astronomer named Richard Carrington was sketching sunspots through his telescope when he observed something no one had ever documented before. A sudden, brilliant white flash erupted from the sun's surface. He watched it happen in real time and recorded what he saw carefully. Roughly 17 hours later, the effects reached Earth. The planet's magnetic field was hit with such force that telegraph systems across Europe and North America failed. Some operators reported receiving electric shocks. Some telegraph lines sent messages without any power connected to them at all. The northern lights were visible as far south as Cuba and Hawaii. People in the northeastern United States woke in the night, convinced it was morning because the auroral glow was bright enough to read by. The atmosphere was alive with color in places it almost never appears. If an event of the same scale struck today, the effects would be different in nature, but far broader in reach. Our world runs on electronics that did not exist in 1859. Satellites, power grids, communications networks. The Carrington event, as it has come to be known, asks us quietly what we have built since then. In 2012, a solar storm of comparable scale did erupt from the Sun. Researchers who have since studied the event believe it may have been as powerful as the Carrington event, possibly stronger in certain measurements. It missed Earth. The eruption traveled through space, along a path that crossed our orbit, but we were not in that position when it passed. Had it arrived just 9 days earlier, our planet would have been directly in its path. A paper published in the journal Nature Communications in 2019 used the term near miss when describing the 2012 event. The authors were careful and measured, as scientists tend to be, but the conclusion was clear. it had been a very close call. What I return to when I think about that 9-day margin is this. The Sun has been doing this for 4.5 billion years. It will keep doing it. These events are normal. They are part of the Sun's ongoing rhythmic life, the same rhythms that have lit every morning you have ever seen. The Sun is not trying to harm us. It is simply being a star. And stars, by their nature, are enormous and occasionally restless. That restlessness, from where we sit, feels huge. From where the universe sits, it is about as eventful as a breath. Part 3. When volcanoes changed everything. Around 74,000 years ago, a supervolcano erupted on the island of what is now Sumatra in Indonesia. The eruption, known today as the Toba event, was among the largest volcanic eruptions in the past 2 million years. Its effects reached across the entire planet. The eruption released an enormous volume of ash and sulfur dioxide into the atmosphere. This created what scientists call a volcanic winter. Sunlight was partially blocked for years, possibly up to a decade. Global temperatures dropped and plant life struggled across vast stretches of the world. Some researchers have proposed that this event may have pushed the early human population to very low numbers, perhaps to just a few thousand individuals in isolated groups. This is sometimes called the Toba bottleneck theory, though it remains a subject of active scientific discussion. If the bottleneck theory holds even partially, it means that everyone alive today descended from a population that may have been smaller than the number of people in a modest apartment building. We are, all of us, the product of an improbably narrow passage through time. There is something quietly humbling in that. The world was remade by fire and ash, and yet something held on. Something small and stubborn and human survived, in scattered pockets, kept going, and eventually it became every person who has ever looked up at the night sky and wondered. In 1815, a volcano named Mount Tambora, also in what is now Indonesia, erupted in what remains the most powerful volcanic eruption in recorded human history. The explosion was heard over 2,000 kilometers away. The ash column reached into the stratosphere. The following year, 1816, became known in Europe and North America as the year without a summer. Temperatures dropped across the northern hemisphere. Frosts came in June. Crops failed. Livestock died. Famine spread across parts of Europe, and communities that had no knowledge of what had happened on the other side of the world had no framework to explain why summer had simply not come. In Switzerland, that same year, a young woman named Mary Shelley was staying at a villa near Lake Geneva with a group of friends. The weather was so consistently cold and dark that they spent much of their time indoors. Her host suggested they each write a ghost story to pass the time. That summer of unnatural cold produced Frankenstein. The connection between a volcanic eruption in Indonesia and one of the most enduring works of imaginative literature in English is not a metaphor. It is a documented chain of events as precise and strange as anything the cosmos has arranged. The universe, it turns out, does not only take things away. Sometimes, through the strangest routes imaginable, it gives something back. A darkness settles over the world, and in that darkness, someone lights a candle and writes something that lasts. Part 4. The Near-Miss War in Space. On September 26, 1983, a Soviet satellite system designed to detect incoming nuclear missiles reported that the United States had launched 5 ballistic missiles toward the Soviet Union. The system flagged the alert as genuine. Protocol called for an immediate response. The officer on duty that night was a man named Stanislav Petrov. He was a lieutenant colonel in the Soviet Air Defense Forces, and his role was to monitor the early warning system and report genuine alerts up the chain of command. That night, the alert looked very real. Petrov made a decision. He judged that the alert was likely a false alarm. His reasoning was practical. A genuine first strike, he felt, would not come in a cluster of just 5 missiles. A real attack would be much larger, designed to overwhelm, not merely to signal. He reported it as a malfunction. He was correct. The system had mistaken sunlight reflecting off clouds for the heat signatures of missile launches. A quirk of the satellite's angle relative to the sun at that particular moment had created a false positive that the system registered as a confirmed threat. No weapons were launched. No escalation occurred. The world continued its business, entirely unaware that one man in a Soviet monitoring station had paused, thought carefully, and chosen not to pass an alarm up the chain. The night stayed quiet. Most people slept. The Petrov incident was not made public for years. It was not celebrated at the time. Petrov was reportedly reprimanded for failing to follow protocol properly, even though his judgment had been exactly right. He went on to live a relatively ordinary life, and the incident was largely forgotten inside the Soviet bureaucracy. He was eventually recognized internationally in later decades. He received several peace awards and was acknowledged by the United Nations. He passed away in 2017. The world's newspapers noted his death with the kind of quiet coverage that befits a man who had saved it without anyone noticing. What strikes me about this story is not the drama of it, though the drama is real. It is the texture of the moment. One person sitting at a console in the middle of the night, making a judgment call. The entire weight of the situation balanced on a single human thought. We carry our worries with us everywhere, and they feel enormous because they are close to us. The things that have nearly reshaped the world have often been settled not by grand systems or overwhelming forces, but by quiet decisions made by ordinary people in unlit rooms. Petrov's night was not so different in some ways from anyone's sleepless night. A problem in front of him, a choice to make, and then, carefully, the right one. The planet moved on. The stars held their positions. Everything continued because someone decided to think clearly in the dark. Part 5. The Comet That Could Have Been. In 1994, astronomers and the general public watched as a comet named Shoemaker-Levy 9 collided with Jupiter in a series of impacts that stretched over several days. It was the first time in recorded history that humans had been able to watch and predict a collision between two solar system bodies in real time. The comet had been torn apart by Jupiter's gravity on a previous approach, leaving a string of roughly 20 fragments trailing one behind another in an elongated chain. When this chain struck Jupiter's atmosphere, each fragment hit with extraordinary force, creating impact scars visible from Earth. Some of the impact sites were larger than our entire planet. Astronomers watching through telescopes saw dark bruises rise up through Jupiter's cloud layers, lingering for weeks before the planet's atmosphere gradually absorbed and erased them. Jupiter wore those marks for longer than most people expected. The energy released in some of the larger individual impacts has been estimated in the range of millions of megatons. To give that some scale, the largest nuclear weapon ever tested by any nation released energy in the range of roughly 50 megatons. The comet impacts exceeded that by a factor of millions. Jupiter is much larger than Earth, and its gravity is immensely stronger. That size and strength make it a kind of gravitational attractor for objects moving through the inner solar system. It has, over billions of years, drawn many things toward itself that might otherwise have found different destinations. Some planetary scientists refer to Jupiter informally as the solar system's shield. The idea is that its enormous gravity acts as a kind of long-range deflector, bending the paths of incoming comets and asteroids over millions of years and steering many of them away from the inner solar system. The extent to which Jupiter actually protects Earth is a matter of ongoing scientific refinement. It almost certainly intercepts some objects. Whether the overall effect is primarily protective, or whether it also, in some cases, redirects things toward us, is more nuanced than simple headlines suggest. But the image of Jupiter as a quiet, enormous presence standing between us and the outer reaches of the solar system has a kind of poetry to it. A gas giant, thousands of times larger than our world, slowly turning in the dark, absorbing things we will never see or know about. The Shoemaker-Levy 9 event made something visible that had previously been entirely abstract. The solar system is dynamic. Things move, things collide. The idea that Jupiter has absorbed impacts that might otherwise have reached us is not a metaphor or a comfort invented for children. It is consistent with what physics and orbital mechanics suggest. When you look up on a clear night and find Jupiter, bright and steady, it has almost certainly earned that steadiness. It has been out there a long time, holding its position, doing what large things in the solar system quietly do, keeping the neighborhood, in the most indirect and impersonal way, a little calmer. Part 6. A star too close for comfort. About 70,000 years ago, a small, dim star passed closer to our solar system than any known star has come in the time that modern humans have existed on Earth. It came near enough to have moved through the outermost region of our solar system, a vast sphere of distant, loosely held material surrounding the Sun. This region, called the Oort cloud, is where astronomers believe many long-period comets originate. It is enormously distant from the inner solar system, where Earth orbits. The objects within it are loosely held by the Sun's gravity and can be nudged by outside forces onto new paths. When a star passes close enough, its gravity can disturb those distant objects, setting some of them moving inward toward the Sun over very long timescales. The effects of such a passage would not be felt immediately. They would unfold over hundreds of thousands to millions of years. The star that passed, a dim red dwarf known to astronomers by a straightforward name, moved through this outer region and continued on its way. It would have looked to any observer, if any had existed, like nothing more than a slightly brighter point of light than usual, barely shifting over a human lifetime. We did not feel it. We could not have. Its gravitational influence, real as it was, played out on scales of distance and time that make our entire recorded history look like a single frame of a very long film. The closest star to Earth today is Alpha Centauri, a system of 3 stars roughly 4 light-years away. The passing star, 70,000 years ago, came within roughly 0.8 light-years, which is considerably closer, though still an enormous distance by any everyday measure. A light year is approximately 9.5 trillion kilometers. These numbers stop meaning much at a certain point, and I think that's actually part of the gift. When scales become incomprehensible, they carry worry away with them. It is very difficult to feel anxious about 1 trillion kilometers. What the near passage of that dim red dwarf reminds us is that the Sun, for all its apparent permanence, is itself moving through space. It orbits the center of the Milky Way. Other stars orbit it. Sometimes, over very long timescales, paths come close to one another. These events are not attacks. They are not aimed. They are simply the result of many things moving in many directions across an enormous amount of space. Occasionally, two of those paths bring two things relatively close together. Then they continue on, indifferent to the encounter, pulled onward by gravity. There is a gentleness in that indifference, once you sit with it. Nothing in the cosmos is targeting us. Nothing has an opinion about Earth or about the small, temporary creatures living on it. We are simply here, and the universe is simply moving. And for now, the two of us are getting along fine. Part 7. The magnetic flip we didn't notice. Earth's magnetic field is not fixed. Over geological time, the poles have reversed hundreds of times. The North Magnetic Pole has become the South, and the South has become the North, in cycles that are irregular and, by human standards, very slow. We are, by some measures, overdue for another one. The magnetic field is generated by the movement of molten iron in the Earth's outer core. As that iron circulates, it creates electrical currents, and those currents generate a magnetic field that extends far out into space around the planet. This field is what deflects much of the solar wind. During a reversal, the field does not simply flip cleanly from one orientation to another. It weakens first, sometimes substantially. Multiple poles may appear and wander. The process can take hundreds to thousands of years, during which the protective field is considerably reduced in its overall strength. A weakened magnetic field means more solar radiation reaching the surface. It means more energetic particles entering the atmosphere. For modern electronics and power grids, a sustained period of reduced magnetic shielding could present challenges that would require significant adaptation. But here is what the geological record also shows. Reversals have happened before, many times. Life has experienced them. Species have passed through them. we have evidence of species surviving, adapting, and continuing on through every reversal in the fossil record, without the wholesale disruption that might be imagined. One reversal in the geological record, which occurred around 42,000 years ago, has been the subject of recent scientific attention. A study published in the journal Science in 2021 examined this particular reversal and its potential effects on the conditions of that time. The researchers found evidence that the reversal coincided with a period of environmental stress, including changes in climate patterns and atmospheric chemistry. They suggested that the combination of the weakened magnetic field and a particularly quiet period of solar activity may have affected conditions on the surface. This period also roughly overlaps with the extinction of large animals in several regions and with significant changes in early human populations. The researchers were careful to say that the reversal was one factor among many, and that drawing direct causal lines is difficult in deep history. What the record does show is that the reversal ended. The magnetic field stabilized in a new orientation. Life, as stubborn and adaptable as it has always been, kept going. The world reorganized around the new configuration, as it has done every time before. The magnetic field is not a fixed, permanent thing. It is alive in its own slow way, shifting and adjusting over timescales that make a human life feel like a single heartbeat. And every time it has changed, the planet has found a new equilibrium and carried on. That is a very old pattern. It is also a very reliable one. Part 8. The gamma ray that didn't reach us. Gamma ray bursts are among the most energetic events known to occur in the universe. They release more energy in a matter of seconds than the Sun will release across its entire 10 billion year life. They are brief, extraordinarily powerful, and they come from the distant universe with some regularity. They occur in two main varieties. Short gamma ray bursts last less than 2 seconds and appear to result from the collision of incredibly dense stellar remnants called neutron stars. Long gamma ray bursts last much longer and are associated with the dramatic final collapse of very massive stars. If a long gamma ray burst were to occur within a few thousand light years of Earth and be aimed in our direction, the effects could be significant. The intense radiation could interact with the atmosphere, depleting the ozone layer and exposing the surface to elevated levels of solar ultraviolet radiation. Some researchers have proposed that a gamma ray burst may have contributed to a mass extinction in Earth's history, specifically the late Ordovician extinction, roughly 440 million years ago. This remains a hypothesis, one that is taken seriously, but not yet confirmed. The key phrase in all of this is aimed in our direction. A gamma-ray burst is not an expanding sphere of energy, like an explosion in all directions equally. It is a focused beam, shaped by the rotation of the collapsing system that produces it. Most of them are pointed somewhere other than us. There is a star system, sometimes discussed in this context, one that sits within our galaxy at a distance of around 8,000 light-years. It is a massive star that shows the characteristics of a system that could produce a gamma-ray burst when it eventually reaches the end of its life. Astronomers have noted that this star's rotation axis does not appear to be pointed toward Earth. If it produces a gamma-ray burst when it eventually expires, the beam would likely be directed elsewhere. We would see the light and energy of the event, but not the focused core of the burst. The word "eventually" is doing a lot of work in that sentence. The star is not about to explode. Stars of this type can remain in their current state for very long periods before the final collapse. The timescales involved are, once again, well outside the range of human intuition. What I find genuinely beautiful about the gamma-ray burst story is how much of the universe's most extreme energy simply passes us by. Not because the universe is protecting us, not because anything is looking out for our well-being, but because the universe is so large that even its most violent events are usually pointed somewhere entirely else. We live in a very ordinary region of a very ordinary galaxy. There is nothing special about our position in cosmic terms. And yet, because the universe is so vast and its events so widely distributed, ordinary tends to be very safe. Ordinary out here is a gift. Part 9. The climate shifts we survived. Over the past 2.5 million years, Earth has cycled through a series of ice ages and warmer interglacial periods with a regularity that astronomers and geologists have traced to subtle changes in the planet's orbit and tilt. The pattern is known as the Milankovitch cycles. These cycles operate on timescales of tens of thousands of years. As the shape of Earth's orbit shifts slightly, as its axial tilt changes by small degrees, and as the direction of its axis wobbles slowly in space, the distribution of sunlight across the planet's surface changes over time. During glacial peaks, ice sheets advanced across much of the northern hemisphere. Sea levels dropped by over 100 meters as enormous amounts of water were locked into ice. Coastlines that are now submerged were dry land. Ecosystems reorganized around the changing conditions. Early humans and the species before them migrated, adapted, and found new ways to persist through each of these shifts. The land bridges created by lower sea levels may have allowed human populations to spread across the globe in ways that shaped the patterns of where people live today. These were not small events. They reshaped continents and rerouted rivers, but they were slow, gradual. They unfolded across timescales that allowed adaptation, migration, and change without the sudden rupture that might otherwise make survival impossible. The planet changed, and life changed with it. The last glacial maximum, the peak of the most recent ice age, occurred roughly 20,000 years ago. At that time, ice sheets covered much of North America and northern Europe. The climate was colder and drier across much of the world, and ecosystems looked profoundly different from today. Humans were present through all of it. We have cave art from this period, paintings on stone walls in southern France and northern Spain that show the animals of the Ice Age world with a care and specificity that suggests people who knew those animals very well. Around 11,700 years ago, Earth began warming into the current interglacial period, known as the Holocene. The ice retreated, sea levels rose, the climate stabilized into the relatively warm, relatively mild conditions that have supported the rise of agriculture and all of recorded human history. The Holocene is unusual in its stability compared to many earlier periods. For roughly 10,000 years, the climate has remained within a relatively narrow range. Human civilization, everything from the first cities to the printing press to the conversation happening right now, has unfolded within that stability. We are a species that has been tested by cold and dark and scarcity and ice. And we kept going, not through power or technology in those early days, but through adaptability, cooperation, and what appears to be an almost unreasonable willingness to persist. That is our oldest inheritance, and it is still with us. Part 10. The Ordinary Miracle. When you add it all up, the asteroid that broke apart over Russia, the solar storms that arrived just days off their mark, the volcanoes that darkened the sky, the nuclear alarm that one man quietly set aside, the comets absorbed by Jupiter, the stars that passed without disrupting us, the cosmic beams pointed elsewhere, and the ice ages we walked through. You begin to see a shape in the data. The shape is not one of a universe trying to harm us. It is not one of a planet that has somehow been favored or protected by anything deliberate. It is simply the shape of what happens when a small world sits in a large, active, and largely indifferent universe for a very long time. Things happen near us. Things pass us. Things brush us. And so far, The combination of distance, timing, planetary physics, and the sheer improbable size of the universe has meant that we are still here, in the dark, talking about all of it. There is something almost mathematical about it. The universe has a certain density of events. Earth occupies a very small fraction of the space those events can reach. Most of them, by simple probability, end up somewhere else. The ones that reach us are, by the time they arrive, usually reduced by distance and atmosphere and sheer cosmic dilution. We are not fragile in the way that the catalogue of near misses might suggest. We are more like a small boat on a very large ocean. The ocean is active and the waves are real, but the ocean is also very large, and most of the waves are somewhere else. I think about the people who have lived through the visible parts of this history. The citizens of Chelyabinsk who saw the sky turn white. The telegraph operators in 1859 who watched their machines send messages without power. The European farmers in 1816 who planted seeds in frosts that should not have been there. None of them knew they were standing at the edge of something that almost went much further. They knew something unusual had happened. They adapted as best they could. They rebuilt what was broken and kept moving forward, because that is, apparently, what humans do. The Carrington event did not end civilization. The Toba eruption did not end the human line. The ice advanced and retreated. The sun flared and quieted. Petrov went home after his shift, and the world kept spinning, without knowing it had been given something irreplaceable that night. Each of these moments is now part of the long story of a planet that has, in every case, continued. The story is not finished. There will be more close passes, more eruptions, more solar storms. The universe will keep being the universe. And we will, I suspect, keep being us. That continuity, that unbroken line of having gotten through things, is not a small thing to carry with you into a quiet night. It is very old and very strong. And on nights like this one, when the world has slowed and the worries of the day feel heavy, it is worth remembering that the line has not broken yet. And on that note, I want to thank you for spending this time with me tonight. We moved through some of the closest calls our planet has ever faced, and what I hope you're left with is not unease, but something closer to wonder. The universe is vast beyond any honest measure. It is active and indifferent and older than imagination. And somehow, through all of it, this small planet has held on. Your worries are real. The things that weigh on you are real. But they exist inside a story that has survived ice ages and wandering stars, and a night in 1983 when one man decided not to press a button. That story is still going. You are part of it, and the cosmos, enormous and unhurried, has no particular opinion about your anxieties. It simply continues, and somehow that is enough.